Hey everyone, welcome to this talk. It's a pleasure to be talking about this new paradigm in interconnect technology called Compute Express Link, or CXL, as you may know it. I'm Arjun Bangre, and I'm the Director of Product for CXL controller IPs here at Rambus. Let's get started. So to begin with, let's look at some of the dynamics that are underway in the data center landscape. I think for all of us here, it is quite intuitive to acknowledge that our data consumption is growing at an exponential rise. Now, a study by IDC pegs the global data sphere to reach 175 zeta billion by 2025. Now, to combat and tackle this explosion of data, the industry is on the verge of a groundbreaking architectural shift. What we see is we are moving from a server as a monolithic unit of compute to more of a disaggregated model where resources can be fungibly assigned based on the incoming workload to match and be more efficient. Now, to go on, if we double click and look at the things and look closely at the data center revolution, we see three important developments taking place in the immediate future. Moving from left to right, if we look at the leftmost one here, we see a transition to DDR5 memory happening right now, which is underway. DDR5 memory is allowing us to expand on the memory capacity, the bandwidth, and power efficiency. Next up, later this year, we'll have host platforms debut, which will support the Compute Express Link, or the CXL. What's interesting with CXL is that if your host has a CXL interface, you will be able to connect more memory through low latency links. So CXL offers support for memory semantics of load store instructions and very low latency. So what this allows you to do, interestingly, is you can add more memory to your processor. Now, this is increasing both the capacity as well as the bandwidth, as you could see. So you have more bandwidth, there are more feeds, and there's more, you can have more capacity by adding more memory. Now, further down the line, we see industry enabling this new architecture of pooled resources. So today, the server architecture has a certain amount of fixed resources, be it compute, storage, memory, GPUs, or AI/ML accelerators. Now, what would be interesting with this varying size of workloads is to have a pool of resources that can be elastically assigned to the incoming virtual machine that is either as it is spun up, it's run and then terminated. All across these three upcoming developments, one thing is something which is common is we have increasing bandwidth, capacity, efficiency, and an underlying need to secure this hardware. Let's understand the CXL protocol a little bit deeper. Now, CXL offers three sub-protocols. One is CXL IO, two is CXL MEM, and three is CXL cache. CXL IO, for those of us familiar with PCIe, is much akin to PCIe. What it offers is a fixed size encoding for packets called as flits. The CXL mem supports the load store memory semantics that I was talking to you about. And thirdly, CXL cache allows your device to have a cache coherent memory domain along with the host. So it enables cache coherency. Now, based on how these three subprotocols are combined, you can have either a type 1 device, which has I/O and cache. So here in this diagram, you can see the host, which has the host memory and cache being connected to a device, which has support CXL I/O on the link as well as CXL cache. We have type 2, which is I/O, cache, and mem, all the three supported by this type of a device. And lastly, type 3, we have just I/O and CXL mem supported. So how would this translate to your use cases? Now, out here on the left is a type 1 device, which is combining CXL I/O and cache. These are typically can be applied to a smart NIC, which would be supporting atomic operations. An example of a type 2 application is either a GPU or an AI ML accelerator. And lastly, a type 3, an application would be a memory expansion device, much like a few slides ago, where I was talking to you about how you could add more memory and hence increase your memory capacity and bandwidth. Let us take a moment now and consider the trends across the compute and memory hardware in the last decade or so. What we find is the processor core counts have increased. I mean, you could recall back in the day from 2 cores to 4 cores to now 48 and even more, right? What we see on the memory side is the memory capacity per core has remained flat. The memory bandwidth per core is actually shrinking, and the memory latency per core is increasing, which is not that a great thing. Now, what we can identify looking at this is we clearly can make out that there is a memory bottleneck here. And solving the memory bottleneck or alleviating it is one of CXL's primary objectives. And the way it does so is by offering 3 value propositions. Firstly, it improves performance. The performance, it does so by allowing you to connect more memory to reflect your larger size data workloads. It increases efficiency because now you have a memory that you can fungibly match to the specific need of the workload. What this translates to is more or better power efficiency. And so what it would equate to you in a data center would be a lower power cost. And 3, it lowers the TCO, and it does so by a better utilization of memory. So when you have a pool of memory resources that can be allocated and deallocated to several different hosts based on where there is a need, it prevents isolation and idle memory being stranded away in the corner, and hence increases the utilization. Some research studies at cloud service providers have already found that this reduces the total amount of memory that is required, total amount of DRAM memory required by 5 to 10%. And based on the size of the cloud service provider, this translates to millions of dollars in cost savings. Now, one of the key things that has enabled CXL to be so quickly deployed in the industry is the fact that it is designed to run on existing native PCIe 5 electricals. Now, by that, what I mean is CXL and PCIe, they both share the same physical layer for transmission. Now, out here in this diagram, you see a CPU which supports both PCI and CXL. And such a port of a device would be called a flex bus port. Now, it is driving the same PCIe trace on the PCB as would have been on a native PCIe supporting PCB, ending up in a native PCI connector slot. Now, what is interesting here is now you can use the same connector slot and accommodate either a CXL device which supports CXL or a native PCI device. Thereby, there is a lot of reuse of existing infrastructure. Now, like PCIe, it supports native link widths of by 16, by 8, and by 4. It supports bifurcation, and it supports degraded widths of by 1 and by 2 as well. Now, CXL is most optimal when run with a line rate of 32 gigatransitions per second. However, it does support down to 8 and 16 gigatransitions per second per lane. Now, when you connect either a PCIe or a CXL device in a slot, what happens is the link training begins with PCIe Gen 1. And based on the advertised capability and the ensuing negotiation that happens, the link can either stay in PCIe or switch over to support Compute Express Link or CXL. So what we see here is in this ecosystem is now we are reusing the PCIe 5, the channel, circuit, and the retimer. Today, we know that some of the leading applications on the cutting edge of technology are memory tiering and artificial intelligence solutions. Now, all of these solutions can really benefit by the advantages of minimizing latency. And so Compute Express Link was built with one of the key paradigm metrics of having very low latency and has hence been adopted by chip architects and system designers. Now, this table shows other standards, the C6 and the PCI Express, that have comparable bandwidths. But if you look at the latencies that are offered by the PHY and the controller together, you will see that CXL offers more than 60% reduction in the total latency. So this is quite something. Now, as with all high-value data, we have now seen that CXL has the applications which carry such high-value data. And with that comes this need to protect this data from attackers. Now, security experts agree that any chip in a system can be a potential target for a physical attack. And the CXL interconnect can be a specific target because of the kind of data that it could carry. And the adversaries which can perpetrate such attacks could use a sniffing device And a sniffing device could take the shape of either a logic analyzer, a purpose-built interposer, a rogue retimer, or a malicious switch. Right? So what we understand here is there has to be a way to secure this physical link against such attacks. Now, let us take a look at the controller IP that we at Rambus have built and have deployed with dozens of customers today, which is the Rambus controller IP for CXL 2.0. Now, the yellow boxes are the boundaries of this top level RTL. And it has two interfaces coming out. One is the user interface, where this is connected to the rest of the SoC's logic. And on the south side here, you have the pipe interface to connect to the PHY or the SerDes, which then drives the signal onto the PCB. Internally, we have the standard layers of the CXL protocol, which is the transaction link layer and the logical subblock. Support the I/O, mem, and cache, and we support two different kinds of user interfaces. One is a native interface, and two is an AXI-compliant AMBA4 interface. Now, just a little while ago, we looked at how securing the data was important. And to do this, we want to be able to build a security engine which is compliant to the IDE specification of CXL, which is integrity and data encryption. But you want a purpose-built security engine that has a low footprint, can do robust encryption, and not add excessive latency to your data path because of encryption. So we have two flavors of the the controller. We can have a controller without or with IDE. And in cases with IDE, the engine is already tightly integrated with the controller. So this controller is designed to the 2.0 spec and is backward compatible. It's based on our field-proven and field successful PCI Gen 5 controller. It's fully parameterizable. It supports native interface and the Intel CPI protocol for CXL mem and cache. It has the LPIF interface implementation here to arbitrate between CXL IO, mem, and cache. And our controllers support both ASIC and FPGA implementations. So if you want to develop a prototype or a proof of concept design, having this flexibility where you can move from an FPGA implementation to an ASIC implementation becomes crucial in kind of wetting out your design and proving your architecture up. So in terms of benefits that our IP can offer you, over and above the feature set, is that our IDE engine is, as I was telling you, is purpose-built with efficient pipelining implemented and can support this mode with zero latency. Yes, it's zero. So zero additional latency over your regular CXL use, right? So, and this, what this translates to is it is about, can shave off this otherwise introduced latency, which could add latency by more than 40%, right? Secondly, we have a scalable architecture where you could configure based on your use case of number of lanes that you are going to support in your link, as well as your pipe interface that you're going to use to connect to the SerDes. The IP supports clock and power gating, and so is very power efficient. Rambus offers an CXL subsystem, which is both a controller and a PHY integrated together. Right? So what we have is a pre-integrated and interoperated tested solution, which uses a controller and SerDes, and with an Express Agent chip debug IP, which is a IP that you can license from us, which gives you visibility into this interface between the controller and the PHY. We provide a complete reference design and test bench and provide a single point of support for all your pre and post silicon queries and consultation. In summary, what we know today is AI and ML applications which are data intensive, and you know they are data intensive as you can see the neural network sizes exploding. Like the GPT model currently has about 175 billion parameters, and so it shows you how it reflects the need for translating or shuttling this data in and out between the compute processor unit and a specialized AI/ML accelerator. And so you need a lot greater bandwidth. Now, CSPs, cloud service providers today spend millions of dollars on DDR memory. And so improving the utilization would save a lot of dollars here, as well as provide efficient ways to manage memory. In addition to low latency and memory semantics, CXL offers cache coherency. And by securing the link with a purpose-built IDE engine, you can make it robust against physical attacks. And by opting in for our solution of the PHY and controller subsystem integrated, your design and process is very much simplified and de-risked because we have done all of this validation for you. That concludes this talk on Compute Express Link. If you are staying on further down in today's set of presentations, I'll be talking about PCI Express Gen 6, and I'll be happy to have you join in that discussion as well. If you haven't already, there should be a pop-up box that allows you to ask any questions, and I'll be happy to take them. At the right side in this webinar platform, you will also be able to download some technical collaterals like product briefs and PDF slides of this presentation. Thank you for joining this presentation with me today, and I wish you a nice rest of your day.